Bonjour à tous. Welcome everyone to the Fruit seminar today. Today we are hosting one of our own. So Serena has been a PhD student in our lab since 2018. Before that, she did her master's in Italy, in University of Bologna. So today she's going to talk to us about numerical methods for control and optimization of fluid flows. So, Serena.
Okay, so hello everyone, and thanks for being here. As Taran already said, today I'm going to talk about what I've done during my PhD. So about numerical methods for control and optimization of fluid flows. So my PhD was done under the supervision of Dr. Sayadi and Professor Frey, and with the collaboration of Professor Fosas de Pando and Professor Schmidt. So first of all, now with advances in computing power and storage capability, we are able to simulate with high fidelity the flows encountered in many industrial applications. But in order to maintain and ensure optimal operating conditions, we need to control and optimize these flows. This is because we need to, with the climate change problems, we need to reduce pollutant emission, reduce acoustic pollutions, and try to get the most of energy from these systems. So how do we optimize a fluid flow? In an optimization problem, we want to modify a flow to match the desired output, so to maintain the optimal operating condition. And mathematically what we do, we define a cost functional, so it's our target, and this is the function we want to optimize. This function depends on the state variable, which is the variable that governs the physical phenomena, and control variables, which are the variable that we use to manipulate the system. Here as an example, we can see how changing the value of the control variable can have an effect on the forcing, in this case in an inlet for a in-cross flow jet that is used usually in a gas turbine combustor for the injection. So for doing this, we have to find the optimal solution for this cost functional, and what happens is that this function can have different shapes, and our goal is to get to the global minimum of the function. The difference between the two is that in a convex function we just have one global minimum, and in a non-convex function we have multiple minima, and we aim to get to the global one. How do we get to the global minimum? We use optimization algorithms. So optimization algorithms are divided between gradient-based methods and derivative-free methods. Gradient-based method, we have an iterative procedure which is based on gradient information. So if this is our cost function in 1D, we start from an initial condition and we move toward the optimum using the gradient. And the computation of the gradient can be done analytically with forward differences or using adjoint methods. For derivative-free method, we still have an iterative procedure, but in this case we want to determine the next candidate points for the optimum without having any information of the gradient. So what we can do is, as an example, we can span a set of points in the design space and then define a distribution, take the best of these points, and then again change the distribution, change the search space until we focus on the region where we have the minimum. Different ways to look for these points are present in the literature. For example, we have stochastic algorithm, population methods with genetic algorithm, neural networks, and many others. So it's the way we look for the new points that define the algorithm nature. These algorithms, of course, they have benefit, also limitation. For the gradient-based method, we have the complication with the extracting the gradient. So for a complex configuration, it's very hard to find analytical solution. And when we work with many design parameters, so in a very big design space, using forward difference is not practical. So we can use adjoint-based methods in which the derivatives are computed with one function evaluation, but on the contrary, this method can diverge when applied to high complex simulations in presence of turbulence for numerical issues. and they require high computational cost given to them by the need of storage, the direct solution, and as we will see later, the need to solve a loop at each iteration. Other than this, gradient-based algorithms do not guarantee the convergence to a global minimum, because the gradient can get stuck in a local minimum and not able to get out of here. Derivative free can converge to a global minimum, but this can require many function evaluation, leading to a high computational cost. So maybe it converge, but it's going to be so long and costly that it's not practical to do it. So the objective of my PhD was to reduce the computational cost of optimization methods in order to apply them to complex problems and couple them with CFD simulation. How do I did that? I used two methodologies. So I used first parallel algorithms and then low fidelity models. So with parallel algorithm, we are able to reduce the computational time, and with low fidelity models, we are able to reduce the computational cost. Both methods can be applied on gradient-based optimization and derivative-free optimization. For parallel algorithm, we can both parallelize on the space and on the time interval of the optimization loop. And I will talk a little bit better about this later. And in derivative-free, what we can do is or parallelize one single simulation, so the function evaluation, or launch different function evaluation at the same time in order to evaluate the function at different points in the design space. With low fidelity models, so we want to use reduced order models, so reduce the dimensions of our problem. And we can both use a reduced order model for direct and adjoint problem when we use adjoint-based method to extract the gradient. But this, of course, leads us to an approximate gradient. And for derivative-free algorithm, we can use reduced order model for the function evaluations, or we can approximate the objective function. So we can approximate the objective function in our design space using surrogate models. So this was for giving a little bit of context. Today, I'm going to talk about the three main projects I developed during my PhD. So first of all, I'll talk about gradient-based optimization, in particular using adjoint, and then I'll show the paralleling time algorithm we developed. Then, for reduced order model, we use, in particular, a projection-based reduced order model, and I will show the results we got with the GNAT method. And then, out of the optimization procedure, we developed a data-driven identification of flow dynamics to identify the dominant dynamics present in a flow. So, let's talk about gradient-based optimization. As we said before, whenever I want to optimize a function, I have to define my I have to define my cost functional. And here we can see the contour of the objective function in a two-dimensional design space. But of course, I don't want just to find the minimum of this function. I want to find the minimum that satisfies the state equation that governs my flow. So in our case, it would be Navier-Stokes equation. So I have to start from an initial condition until the optimum, laying on the constraint. And for doing this with adjoint-based method, I have to include my constraint in the objective function. We use a variational approach, so we form the Lagrangian and we include the constraint in the objective function, adding some Lagrangian multipliers. So at the end, if I want to find my minimum, I have to basically find the derivative of this Lagrangian with respect to the design parameters. For doing this, we take the Lagrangian and we take the variation with respect to the independent variable equal to 0, and we form the optimality system. So we get the state equation, the adjoint equation, and finally the optimality condition, which can be modified using the adjoint equation to get to the gradient. As we can see here, the gradient depends on the adjoint, which depends on the direct solution. So we need to solve the three equations to finally get to the gradient. So once we had the gradient, we can move towards the minimum using iterations. When we use adjoint-based optimization to compute the gradient, each one of these iterations needs to solve the direct problem, so the function evaluation or Navier-Stokes equations, and the adjoint problem forward in time. So when we use unsteady simulation, we have to move from T0 to T final. Once we know the solution of the direct problem, we can linearize and form the adjoint problem to solve backwards. The challenges of this procedure is that, of course, it requires many iterations. Then, as we said, the direct and adjoint are solved sequentially. And so when we work with unsteady problem, we need to get to the gradient, the time is at least 2 times the time needed to solve the direct equation. So, to reduce the time of the optimization loop, we decided to use parallel time algorithms. So, parallel time algorithms were first introduced with Numerical in the 1964, and they're usually used to accelerate the direct problem. In this project, we decided to use parallel time algorithm to accelerate the resolution of the direct adjoint loop, both of them. So how do we do this? We use the parallel time algorithm proposed by Skin in 2021. So we have our minimization problem, our optimization problem, so we have the functional and our constraint. Since now we are using a Navier-Stokes equation, we have an algebraic differential equation due to the incompressibility constraint. So usually what we do, we start from time 0 and we integrate the function until the final time. Here we want to parallelize the resolution of this problem. So we form the adjoint equation, which is as well an ADE. And then we start saying, okay, we solve the direct problem still in serial, but we define a time partition on different processors. Then the adjoint equation is split in inhomogeneous and homogeneous counterpart. So then we can start integrating the inhomogeneous equations with 0 initial condition as soon as the processor 1 finishes the resolution of the direct problem. When we are here, so we have everything we need to integrate this equation on this time partition. So while processor 2 is integrating the direct solution, processor 1 can start integrating the adjoint, inhomogeneous adjoint solution, and so on. So processor 3 goes with the direct, and the 2 processor keep integrating backwards until the end, in which we have to wait a little bit of time here. Then that's the 3 processor here finish to integrate the inhomogeneous equation. As you can see, the time partition is non-uniform in order to reduce this waiting time we have here. Once we are here, we have the initial condition here to be able to solve the adjoint homogeneous adjoint equation. Then now carry on the information about the initial condition. Sorry. And to increase more the gain we get with this algorithm, we can integrate the homogeneous equation using exponential time integrator. So since we are working with an ADE, we have to perform an additional projection step to be able to incorporate them, include the divergence-free constraint in the momentum equation. So now that the algorithm is been showed, I show you some results. So we perform the first steady actuation, where steady means that our control variable do not depend on time. And we applied this algorithm on the flow around the cylinder at Reynolds 200. And in our code, we have inverse boundary, meaning that the surface of the cylinder is represented by the Lagrangian points. So I can fix velocities at the Lagrangian points. And these velocities are going to be my control parameters. So I want to find the configuration of the velocity at the Lagrangian in order to reduce the drag of this flow. So we start the simulation. When we arrive to a stable oscillation, we start the actuation. And we can see in the red lines is the control drag coefficient. We can see that we can reduce its magnitude, its oscillation, and a little bit also its phase. But in this context, we are interested more in the time performance of the algorithm. So here in this graph, I show the time needed to solve the serial forward problem, so without the adjoint, without the computation of the gradient. On the top, I solved the direct adjoint loop in serial, and with the red, I increased the number of cores using the parallel algorithm. So we can see that we can reduce of 94% the time needed to compute the gradient, meaning that when I use a parallel algorithm, by the time I have my function evaluation, I wait just a little bit more, and I also have my gradient. When we work with unsteady actuation, the situation changes a little bit because now my control depends on the time. So we built a toy problem for this. So we are trying to simulate what happens in a stage of an axial compressor. So it's very simplified. We take a channel, periodic boundary condition, and we use inverse boundary to build a wall. And to simulate the rotation of the blade, we move the lead. So the lead is moving with the constant and uniform velocity, and we want to reduce the total pressure loss in order to reduce the vorticity at the tip of the blade. So for doing this, we decide to introduce a Gaussian-shaped roughness at the top of the system that moves uniformly with the lead. To avoid changing the shape of the boundary, we decided to use dynamic roughness method to introduce this roughness, which is not physical in this case, but we manipulate the velocity at the top boundary in order to simulate the effect of the presence of this roughness. So we approximate this roughness with the Gaussian, and the control parameters now are the height and the width of the roughness. So we have the vorticity field and the pressure. So we know that a non-well distributed pressure here at the back and in front of the blade form vorticity at the top of the blade. So we can see in the control configuration that the pressure now is better distributed, and the vorticity is not reduced in magnitude but in phase, so we will have less impact on the back of the blade. Also in this case, we are more interested in the performance of the algorithm. So same as before, here I'm showing the time needed to solve the serial forward problem and the serial forward adjoint problem. And in red, we have now the reduction for the time computation of the gradient. And here we can reach the 58%. This is because now the optimality condition, so the equation we need to solve to compute the gradient, is time dependent. So we are adding a dimension to the matrix. But this is very good already. So by the end of this project, we managed to apply parallel algorithm on Navier-Stokes equation. I didn't talk about this here, but to include the constraint in the momentum equation, I had to perform a projection step in order to be able to apply exponential integrators on Navier-Stokes equation, adjoint equation. And then we used Krylov subspace to perform the exponential integrator. And we proved this algorithm both on steady and unsteady problem, showing good results even if we're working with this small optimization problem. So now we were able to reduce the computational time, still maintaining a high computational cost because we are using more cores. When we talk about reduced order model, now we want to reduce the dimension of the problem. So how a projection-based reduced order model works? Very simply, as much as I can. So we take the high dimensional problem and we want to project it on a lower dimensional subspace spanned by some set of orthogonal bases, where the dimension of the base is much smaller than the dimension of the high dimensional problem. How do? We perform a Galerkin expansion, so we approximate our state vector, so our solution, with a linear combination of spatial modes. And so then we can build a reduced order system of equation where now the unknowns are the temporal coefficients. In this case, now we have n nonlinear equations and nw unknowns. So we have to add constraints, enforcing the orthogonality on another test subspace, and finally we are able to get the generic reduced order model with two spatial bases, and the unknowns are still the temporal coefficients. So when the two bases are the same, we talk about Galerkin projection. When the two bases are different, we talk about Petrov-Galerkin projection. The bases are usually computed using snapshot POD. So, fast illustration of snapshot POD. I take my temporal, my time history of the data. I plug them in a matrix, perform SVD, and I'm able to get the POD modes and the singular values, which are in descending order. When we use the full matrix, the approximation is accurate, so this isn't equal. Or we can truncate the basis in order to reduce the dimension of the system, and of course we have some approximation error in this case. So the most common method used for reduced order model based on POD projection is Galerkin projection, but since we are truncating the model, we have some issues with the instability, and we lose information from the truncation of the basis about the nonlinearities, because we are performing a linear combination of linear modes. So what we do here, what I've done during my thesis, is to use the GNAT, which performs a Petrov-Galerkin projection, and it performs a second step. So we have a second optimization problem, which is called hyperreduction, in which we are able to bring back some information lost with the truncation of the basis, and we are able to reduce even more the dimension of the model. So the method works like this. We start with high-dimensional model, and we collect the snapshots using incremental strategy. So instead of reducing the mean, of removing the mean, which is done usually in literature, we remove the first time solution, and from this we can compute the POD. Then we go to a Petrov-Galerkin projection. We have to solve the least square problem, and we solve it using Gaussian iteration. But at this moment, these metrics still have the dimension of the high-dimensional model. So what we can do is that we collect snapshots for these two quantities, which are the column-reduced Jacobian and the residuals, during the Gaussian iteration, and we compute POD of these two tensors to approximate them further in their relative subspaces. So when the tensors are approximated, we can build these matrices. I'm not getting into the details, and we get to the online reduced order least square problem, which now has the dimension of the points we decided to approximate the tensors on. So I'll show you very quickly some results. So we applied again on a flow around the cylinder at 20-200. We collect the snapshot, then we perform the SVG, and we can see here the singular values and the first four modes. Here, notice that since we're using the incremental snapshot collection, these modes are not perfectly symmetrical with the X, and the singular values are not coupled. Then we select some points in the domain to perform the tensor approximation. So what we do, in this case, we used 300 points, and since we are in a staggered grid, we modified the algorithm in order that when the algorithm picks the central points, automatically we add to the vector also the horizontal and velocity, vertical velocity of the same cell. So running the greedy algorithm on that flow configuration, we're able to find 300 points that are on the wake, especially at the boundaries of the wake where we have the most nonlinearities, and they're based on the basis built on the residual and the Jacobian snapshot collected during the model 2. So we were able to reproduce the flow everywhere. Here, as a simplification, I show the reproduction of drag and leaf coefficient, which are found from the velocity at the inverse boundaries. And we reproduce two shading periods, and so we get good results. I don't know if it's clear, but the curves almost totally overlap. Noticing that we have no greedy points on the cylinder surface. So basically, the model 3 has no information on what happens on the cylinder, other than the POD modes we collected at the beginning. So I talked about model reduction mainly to justify what's coming next. So here we use the GNAT method, and we had a dimensional reduction of order than 90%. This is of course a very simple flow. I didn't talk about this here, but of course the reduced order model is not adaptive to parameter changes. So what we've done is also we introduced the interpolation on Grassmann manifold and its tangent space in order to have a reduced order model that can adapt when we change the parameters on the design space, so eventually to apply that to optimization problems. And so we talked about greedy algorithms to look for these points, but the cost of this algorithm can be reduced, restricting the search domain. So just to the nonlinear regions, and this motivates the next topic, which is the data-driven identification of flow dynamics. So when we talk about equation identification, our goal is to discover a governing equation from data. In this case, we have differential equation. On the right-hand side, we have a nonlinear term. And we want to approximate, basically we want to discover the form of this nonlinear term. So what we do a collect time history of data again, then we build the derivatives, and we can say that the nonlinear term can be approximated with a linear combination of candidate functions. This candidate function can have whatever form we want. So we can build a library of candidate function, which can be linear, nonlinear, trigonometrical, many forms. And once we have this library of candidate functions, so we can rewrite the nonlinear term as a linear combination of this candidate function, where these coefficients tells us which one of these terms is active in my equation. To have a graphical representation, so here if I have two variables, I can go up, in this case up to the second order, and these coefficients, there can be 0 or not, and when they're not 0, they tell me that the linear or nonlinear term in the library are active or not. So why do we use this? We want to identify the active term of the library of candidate function, which, when we talk on Navier-Stokes equation, represents the different dynamical behavior of the flow. So how do we do that? We want to then to discover the dynamics and to cluster them together. Okay? So we perform again a snapshot collection. As I said before, we pick some random points in the flow. In this case, I just show 3, but we can span the whole domain with points. And then we perform linear regression on each one of these points to find the dominant contribution of each term of the Navier-Stokes equation. So for doing this, I move in one point. I use the neighbors to build the spatial derivatives, and also I build the temporal derivatives before. And then I create a library of candidate function, and I decided to use the library containing the terms we have in Navier-Stokes incompressible equation. And then we go to linear regression. In this way, each one of these points will be defined by a set of coefficients, both for the equation for u and for the equation for v. At this point now, each point is defined by a set of coefficients. Here we can see an example of different points, one being the back of the cylinder, one being in the wake, and one being in the free stream. We can see that different coefficients are activate the terms in the Navier-Stokes equation are different, also in magnitude. So once we have each one of these points defined by a set of coefficients, we can cluster the points based on these coefficients. For doing this, we use a community identification strategy, which is given by the Licht-Newman network. Very quickly, what is a network? Is a structure comprised of node edges and weights. So we can represent it practically like this. And mathematically, we have the adjacency matrix, that which elements are 1 if we have an edge from one node to the other, and 0 otherwise. Licht-Newman network is a directed graph, meaning that my edges now also have direction. We can have multi-edges, which here are represented by thicker lines, and we can represent in the adjacency matrix with weights. And we allow self-edges or loops, so as here in the node 1 and node 2. The matrix now looks different, so we have weights instead of 1. The matrix is asymmetric given to the fact that we have direction, and also the diagonal is not null because we have self-loops, and the self-loops are on the diagonal. So here we have symmetry, and here not. So once we have the adjacent symmetry, we can feed it to the Lich-Newman algorithm to discover communities. So we want to maximize the modularity. The modularity is a quantity which was introduced by Newman, which is the fraction of edges that we actually have in communities minus the fraction that we expect to have statistically. Okay. So, for example, here we can have two nodes connected by two edges. We can see that A to B has a bigger weight, meaning that this is statistically probable. But if we have B to A, and this is existing in our network, it's statistically surprising, giving a higher contribution to the modularity. Okay. To divide this graph in different communities, we use spectral optimization method from Newman very quickly. So we rewrite the modularity with the modularity matrix, and we want to find the S, where S is a vector of +1 and -1, giving a label to each node. So +1 is a community, -1 is another community. And we can rewrite this modularity with eigenvalues and eigenvectors. So basically, at the end, we want to find the vector S, which is the most parallel as possible to the vector, the eigenvector of highest magnitude. Once we finished assigning labels to each node, so +1, -1, according to the direction of the eigenvector 1, we do a fine-tuning step in which we move nodes from one community to another to check if we can increase even more the modularity. And at the end, we have the graph divided by 2, and we can repeat this algorithm until we get to the optimal configuration. So in this case, for example, we can do a first bisection, and then we work on this community again, and we cut again until the modularity is maximized. The positive aspect of using Lich-Newman network is that the number of communities and their size is not decided a priori. So to validate the community identification strategy, we use a statistical model on the dynamics of the turbulent wake. So this was proved by Rigas in 2015. So he did some experiments on the flow around a bluff body, saying that the symmetry of the turbulent wake around this body, behind this body, depends on the position of the pressure, center of pressure, which is the average position of the pressure at the back of the bluff body, with respect to the center. So when the center of pressure lays in the center, the wake is symmetrical. When it moves from the center, it is not. What we want to do is to use a Lich-Newman algorithm to identify communities for this equation, which is a two-dimensional Archimedean equation, and for the trajectory of the center of pressure. But this is mathematically not interesting for us. So we modify the Langevin problem a little bit to add a nonlinear term in the phase, because we are symmetrical in the phase here, in order to enhance a bimodal behavior. And now we want to discover these two communities using the Lich-Newman algorithm. So we solved the Langevin equation. We have the time history of the position of the center of pressure in Cartesian coordinate. We initialize the domain with subcluster, spatial subcluster. Each of these clusters will have a density of the position of the center of pressure, and then we want to build this graph. So in this case, each cluster is a node of my graph. Every time that my center of pressure moves from one cluster to the other, we have an edge, a directed edge. When it moves back, we have a directed edge with the opposite direction. When it stays in the cluster, we have a self-edge. So having the graph, we have the matrix that we can fit to the Lich-Newman algorithm, and that's what we get at the end. So we are able to identify communities among these clusters, and then we can find something that is very similar to the PDF we've seen before. Of course, here we're using casual, not regular clusters, and but we can still find a high density regions. And now we also have some information about how the center of pressure moves from one little subcluster to the other. If we want to have this figure perfect, we should use Cartesian subcluster, very small, as the beams of an histogram. Okay, this was just to validate the Lich-Newman algorithm, because now we want to use it on the random points we have picked with the algorithm. So, as we said, each point is now defined by a set of coefficients. So each point is a node of my graph. What we move to the coefficient subspace, and we compute Euclidean distance between the points. So we can create the adjacency matrix according to the relative distance between the points, and we create links. So points that are far away to each other in the coefficient subspace are not linked. Points that are close, they have links. And then, with the Lich-Newman algorithm, for this flow, we can find 3 big clusters. So we have one cluster on the wake, one cluster for the free stream, and one intermediate cluster between the two. This was expected, but the interesting thing is that other than finding the clusters, we can also find the links we have between clusters. So we can see here in the matrix, if you can see, how the cluster points in different clusters can communicate with each other, even if they're not identified in the same cluster. So, as we expected, orange and purple, they communicate a little bit more, while green and purple, they don't communicate at all. So, we have nice results here. Why this can be, how can this can be used for reduced order models? If I take my cluster distribution and I compare it with the greedy algorithm I used before, I see that the points that the greedy algorithm selected are the points that are in a nonlinear cluster, so behind the wake. So what we can do before deciding if we want to use this reduced order model, or if we are happy just with the simple Galerkin projection, is to check if we have nonlinearities, what kind of nonlinearities we have, and to restrict the search domain for the greedy points to the nonlinear area, reducing, of course, the dimension of the matrix that we use in the optimization problem for the Gauss-Newton tensor approximation. So, having more insights on the dynamic governing a flow can help us with the selection of the reduced order model to use, and to identify the nonlinear regions to facilitate the greedy point search. Additionally, for an optimization point of view, this can also help with sensor placing and the selection of control parameters. So, little conclusion on this project. So, we used Lich-Newman network to identify different dynamics in the fluid system. We validated using a stochastic trajectory of the center of pressure behind a bluff body. Then we coupled the Lich-Newman network with a linear regression step to identify the active coefficient in Navier-Stokes equation. This can help us both with the use of reduced order models, sensor praise, and selection of design parameters. But of course, this was a very simple flow. We are not finding anything new. So we have to apply this algorithm on more complex fluid flows, eventually in presence of turbulence. And so, to close the talk, so we were able to explore different strategies to combine CFD with optimization, both reducing computational time and computational cost, using low-fidelity models, enabling multi-fidelity optimization. Of course, this was just a developing phase. We have to test this algorithm and extend them to more complex configuration in 3 dimensions. And the very optimistic perspective is one to have a code which is able to pick which optimization method to use, and if use reduced order models or not. And thank you for your attention.
Any questions? Yeah.
Say more about the construction that we use for the mobile.
How they couple the modes? So we basically have a linear combination of modes. So once we have this equation, we can use this approximation to substitute in this case in Navier-Stokes equation, for example, and then we have a reduced. What? Yes, but since we have a linear combination here, we are losing some of the information of the nonlinear terms. Ah, I didn't put the reference. Yeah.
Any other questions? I won't ask you any questions, Serena. Then that would be weird.
I can ask you some questions.
Yeah? Yeah?
Yeah, so basically okay. Yeah. Yeah, I mean, eventually, if we are able to have data from more complex flow, we can test both, so the reduced order model and the dynamic identification, and check if they agree at the same thing. So the dynamic identification says we cannot use a reduced order model then, just by your hours of computation. Yeah, it probably keeps going there. But actually the thing with this case is that not how you physically would do that, because we are using an unsteady optimization, right? Versus a steady actuation. What you do usually is use an unsteady optimization that, according to the phase of the oscillation, governs blowing its action at the top or at the bottom of the thing. So this is just to show I mean, we're not very interested in the reduction of the drag, we're interested in the performance of the algorithms, just toy problems to validate the problem.
And also, very interesting that these times
No. No, basically, you're talking about the non-uniform. No, they're computed. So the direct problem is still computed in serial. What happens whenever I go to the border here, I take my last solution and I communicate to the second processor. So the numerical solver is the same. I just split on different processors. So while processor 2 and 3 are going on with the integration of the direct problem, processor 1 is free to start iterating backwards. So by the end that the direct problem is solved, I already have the solution of all the inhomogeneous adjoint equation. And at this point you say, okay, but you still have to integrate the homogeneous. But since they're homogeneous, I can integrate them using exponential integrator, which is pretty fast. But actually what gives us the speed up is the application of the exponential time integrator. Because first, before developing exponential time integrator, I was running the problem using the same solver, and it wasn't that good. Like the time performance wasn't that good as here. I don't know. I think so. I think so. The thing is that what I've done here are very small problems. The final goal is to implement spatial parallelization, and when the spatial parallelization saturates, adds also temporal parallelization in order to go faster and faster. So with GPUs, maybe it's even better. Why not? Not for this problem, honestly. The simulation runs in 2 minutes.